All right, one more minute. Two assignments and turn them in. And of the 45 students in the class, still registered in the class, 38 of you did that. And I consider that quite good, really. You turned in both assignments and I received everything I needed the way I needed it. A couple of you buried them in the email. I prefer that you send it as an attachment, but I still got it anyway. Some of you took photographs. That's okay. If you together and wrote the answers on it. That worked for these assignments, but it won't work for some of the more additional assignments that we go through. So try to find a way to just work on the sheet and send it to me. But I was very pleased with what I got. The ease with which I was able to open it up, print it, and file it. I'm a little concerned about the 7 that haven't turned in those assignments, because for those of you who have, I consider you active in the class now. And the others, I'm not sure about. I want them to be active. I'm in no hurry to exclude them or drop them. If any of you know anybody who hasn't turned in the assignments for whatever reason, please have them do so. Please have them get in touch with me. I want all 45 to succeed and to work this out. So while the percentage, I think 38 out of 45 for the first week is really quite good, I want 100%. If anything you could do to help with that, fine. Let's get the other 7 on board. Basically, what will happen is you will send me an assignment. I will open it up, I'll print it out, and I'll grade it right there on the spot. Is that Barton? I'll grade it right there on the spot and give you some feedback. If I need you to change something or add something, who am I gonna have to mute on that? Because we're getting a lot of background there. Hang on a second. Okay, can you hear me now? Can everybody hear me?
Yeah.
No, okay.
Yeah.
All right, again, as I say, I will grade the sheets when they come in and give you some feedback. For example, on the first one, which we'll go over in a moment, in the color code, a few of you missed the problem number 4. So I'll just tell you to do it over again, see what you can do. 2 things. Most of you are going to get 100% on what you do. because that's just the nature of it. You build something, you put something together, it works, then you get the full points. What's the fiddle with? So you get 25 out of 25 is the typical thing, 30 out of 30. That's the way it's going to be. And so you might say, well, that's great. That means everybody gets an A. Well, it doesn't work out that way, though if it did, fine. I'll give you the grade you deserve. I don't care about any, the others. I don't care how many A's I give out or anything like that. But it doesn't really work that way, because what happens is where you wind up getting less than an A is in not turning in all the assignments. It's the number of assignments. If you're in class every day, every week, and turning in these assignments, you'll do fine. It's the ones that, out of 35 assignments, they've done 25. Whatever reason, that's where the grades will slip. So again, you stay on top of it, you do these assignments, you should be fine. I will find a way to summarize your grades and send them to you at a regular basis. I'm working on that now. But at the same time, when you turn something into me and I grade it and return it to you, I'll just give you the points right there. So you might write those down and put them somewhere. And you can always email me. You can always say, look, I didn't get, what was the grade on assignment number 4 or for week number 4? And I'll just send it to you. But I will try to do that, and we'll do it on a regular basis. Okay. I'm just trying to look at a few things that we need to do. Okay. I always like to show a little project at the beginning. I used to do that in the in-person class, because I told you I have 100 of these, or close to 100. But I don't know how well that will work, but here's a little one that I could show you here. This is a spinner. You've all seen these. Your little brothers and sisters probably have these things. They're kind of cute, relieve tension and all that sort of thing. Well, this one I made, and you can make these, and you open it, you have to solder the little components inside, so forth. It's a little tricky. This one has LEDs. I don't know if you can see this very well, but when you spin it like this, at night, this really looks a lot impressive. You have about 4 different LEDs spinning at different speeds and that kind of thing, and it's kind of dramatic. And again, you made it yourself, so it's just one of those projects where you can spend all time doing that. Usually what happens when I demonstrate these in my in-person class and it's working, the students clap. But I guess if you're not going to do that, that's okay. So, okay. How are you guys doing with tools and materials and stuff? And there are still 2 boxes to go out today for whatever reason. I have 2 boxes that will go out today. I wanted to send them yesterday, but that was not possible. Okay. Okay, so let's take a look. And again, if anything's not working here, let me know. Let me know. Let's go to week 1 and let's just catch up and see if there's anything that needs to be said about the assignments. And I think there is. With the code exercise, you did well. You did very well on this. No problem. But this is a 4-band resistor color code system. Most of the charts that come around show a 4-band and a 5-band. Forget the 5-band altogether. You'll rarely see it, and we're not going to talk about it now. I gave you a little URL to look at. It wasn't the best one I've seen on the color code, but it was okay. And here's your chart. You see, it's too complicated. I want this 5-band stuff. I put a big X across it like this. But I think you've got it, except for number 4. A few of you had a little problem with number 4. It says, what are the 4 color bands for a 680 ohm resistor with 10% tolerance? And the color bands are 6 is blue, 8 is gray, and there is 1 0 here. And what is 1 in the color code? What color is 1? Anybody? Yes, it's brown. So the answer here is blue, gray, brown. A few of you put blue, gray, black. Black is 0 zeros. So when you look at this again, you have a numeral 6, which is blue, a numeral 8, which is gray, and this is not nothing. This says, oh, there is 1 0, and that would be brown. So you have blue, gray, brown. What if you had blue, gray, black? What would that value be?
68.
68.
What's that, Anastasia?
68.
Right, 68. You would have a blue for 6, a gray for 8, and then 0 zeros. Black means no zero. Black means stop with the 8. There's no zeros. Black is a way to bring it below 100 ohms. So black will be there. We always have 3 bands. We always have 3 bands to describe the value of the resistor, the nominal value. We can't, you could say, well, why don't you just stop with 2 bands then? No, that's not the way it works. And a 4-band resistor will always have 4 bands because it will have the first 3 for nominal value and the 4th one for tolerance, with one interesting exception. With a 5% tolerance, you have gold. With a 10% tolerance, you have silver. And you can go through your entire lives, your young lives now, and that's all you'll see is gold and silver. May that be in your life, gold. But there was a time when they made resistors with a 20% tolerance. Horrible things, too wide a tolerance. And the color for that was, there was no color. They didn't have a 4th band. So if you're tearing apart old radios out of the 1930s or 40s, and you come across a resistor that has only 3 bands and no tolerance band, it's 20 plus or minus 20%. Again, you could go through your entire life and never see one of those. Any questions about the color code? Okay, good. And again, do pipe up and let me see it and do something. Okay. All right, let's just take a look at the K&M. I think almost everybody got all of that right. I mean, we're going to have another lesson on this metric conversion in a few weeks. It's more complex, but this one is basically converting K to M. Oh yeah, there are a couple. Remember, K is 1,000 and K means to move over 3 places. It doesn't necessarily mean 3 zeros. It means 3 places. So if you have 47K, you do move over 3 zeros for 47,000. But 4.7K, you still move only 3 places, but this 7 takes up 1 place. So you're only adding 2 zeros, but you're moving over 3 places. And the same sort of logic is with mega. Mega, you move over 6 places, 22 million, 6 zeros, 5.6 meg will have 5 zeros because the 6 takes up 1 place. Are there any questions about that? I think most of you did well with that too. Most of you did well, you're on your way. This is good. Let me go back up here for a second and say, I do have some announcements that come through. I've set it up for 3 announcements so that they drop out as we add more. Once again, I mean this, check your email and your Valley College Canvas site every day. Notice there will be some changes and things that will change. In this particular case, nothing you see so far, but I may add a few something. Now, there will always be Zoom summaries. This is a Zoom summary for the first meeting, which started on September 1st, and this was the Zoom meeting for the one that went to the 3rd on the Thursday. I would suggest, even if you're here, as all of you are, that you read the summary anyway. I add some material to it. I explain a few things, so check that out. And again, always read this first. Okay, so I think we're moving to then, and it says soldering, and that's what it's about. But basically, we're going to do two things this week. And I'll open up this, read this first, and kind of explain that. Okay, so it says this is going to be a hands-on week with lots of making stuff, which I imagine you'll want to do that, including today. I mean, you'll see what we're talking about. Okay, so basically you're going to be working with this solderless circuit board. That's what we're going to do first, and that's this little board that you received in your packet, and the larger portion, which I'll show you in just a bit, that will that you'll have. That's what I'm talking about. Solderless board. It's also a breadboard, and I have a video you'll see in a few minutes that explains why the breadboard thing. Okay, there's an activity. You will construct your first solderless circuit. You're going to do your first circuit today, or you start, with us today. This is an activity, and it's an important one because it'll teach you how to use this board. And it's very important that you learn how to use this board because you're going to be using it more or less constantly. There's solder. And as I mentioned before, in the past, what we did with this practice solder is I would give everybody some solder. I would give everybody a few resistors and a couple of integrated circuits and a printed circuit board, a blank printed circuit board, and I'd show them what to do. And then for a class period, they'd practice their solder. And it worked, soldering, and it worked out all right. Well, again, I discovered that I still had these solder kits that you receive, and it's much more than that. It's much more than that. And maybe it's too much. I don't know. Maybe it's too much. But I don't want you to stress about it and so on. This is practice. You're going to practice soldering. There's only one worksheet that you turn in with this, and you just answer a bunch of questions. I may never see what you've actually soldered. You may want to show it to me. That's fine. But I guess what I'm trying to say is you take it slow. If you don't finish it this week, by all means, drag it into next week and the following week. That's perfectly all right. You're just learning to solder. Some of you will do better at it at the beginning than others. All of you will come along. Again, have fun with it. Learn about it. Practice. Don't stress it. I'm not going to take it in my hand and grade it on the basis of solder connections and so on. You'll know a solder connection when you. And we'll talk more about it today. I mean, we'll get to that. Okay, so that's the. Who's that pretty girl in the back there? Oh, that's my wife. Okay. We're having some work done in the house, some fault flooring done. It might be a little noisy. Okay. It says here how many solder circuit board works, and I'm going to come back to that in a moment. I'm going to go to this one right now. And this is your first solder board activity. This is a sheet that you will turn in when you're done with it. And let me just try to pull this a little further. We're going to look at this in a moment at this URL. I explain a little bit about what the board is, but the URL is really a good one, and it's going to show you what to do. Here's what it looks like. Here's what you can build. I'm going to show you a couple of projects I built on it. This is a schematic drawing. This is your first one. A schematic drawing is one in which the components are represented by symbols that you will come to know. There aren't that many, believe it or not. A dozen will get you 5. But this is a schematic drawing, and from this, I expect you to build your first project on solderless circuit board. I'll explain how that works in just a bit. It so happens that this video you're going to see in just a moment actually builds the same sort of project. So I'm going to click on this now. And what I do with these is once I pull them up, we'll see them. And I would suggest you might want to take some notes, because I'm going to look at them and I'm going to stop it from time to time, quite a bit actually. And the trouble is, some of this comes up with too much stuff, and I noticed that. And this is not the one we want. We want this one here, how to use solder, how to use a breadboard. So you might make a note of that. So it runs about 12 minutes. This is the one you want to click on. You're going to look at it. And I suggest, you know, after this, you look at it again. So I'm going to click on this. I'll open it up like this. I'm going to run it like this.
Hi, this is Ben Finio with Science Buddies, and this video is
We'll go through this. And again, I will stop it from time to time to make some comments. Can you see this? Are all of you okay with what we've got here?
Yeah.
Yes.
Okay, good. So again, you should probably have a board in front of you. It might be nice if you had some solderless circuit board in front of you, either the small one or a larger one. You don't have to, but you know, it'd be nice. This is I think, a pretty decent video. So let's see what's going on here. We don't want that.
an introduction to how to use a breadboard. This is a breadboard. It's a rectangular piece of plastic with a grid of holes that allows you to easily and quickly build electronic circuits by pushing electronic components into the holes. For example, simple circuits like this one with a battery and an on-off switch to control a light.
Now that's what you're going to build. You're going to build. That's exactly what you're going to build today. I mean,
you can also build more complicated circuits. For example, lights that flash automatically, or robots of all different sizes. There are far more examples than we can list in the beginning of this short video. At this point, you might be thinking that it doesn't really look like it has anything to do with bread. The name breadboard comes from the early days of electronic circuits when people would literally use wooden boards with screws or nails driven into them to make electronic connections. Modern breadboards are made from plastic and come in all shapes, sizes, and even different colors. The most common sizes you'll probably see are full-size.
That's the one right there that you expect you to get.
Breadboards, half-size breadboards, and mini breadboards. Larger and smaller sizes are available, and many breadboards come with tabs and notches on the side that allow you to snap together. But a single bread will be more than sufficient in most beginner projects. Let's take a closer look at how a breadboard actually works. The holes of a breadboard allow you to easily push the leads or metal legs of a component like this LED into them, and then will lightly hold them in place. This connection is strong enough that the LED won't fall out on its own, but light enough that if you make a mistake, you can easily pull it out and put it in a new location. Technically, these are called solderless breadboards because they can make these connections without using solder or melted metal to permanently bond electronic components together. Let's find out how breadboards can hold on to components without using solder. If you flip a breadboard over, they come with an adhesive backing that allows you to permanently stick them onto a project. For example, the breadboard stuck to this robot. If you remove that backing completely, like I've done with this breadboard here, you expose a series of metal strips that are inside the breadboard. These metal strips are what make mechanical and electrical connections to the components you insert into the breadboard. We can remove one of these metal strips by pushing it out from the front to see what it looks like up close. Each strip is
And this is the key. These metal strips are the key.
a series of 5 clips that line up with the holes on the breadboard. When you push a component into the breadboard, these clips are what's actually grabbing onto the leads, like you can see here with this LED. This breadboard is made from transparent. You can see the clips from the outside. When you press a lead into one of the holes, it's just getting grabbed onto by one of these clips. Let's take a closer look at the writing on the front of your breadboard. Your breadboard has columns labeled from A through J and rows that start with 1 and go up to a number that depends on the size of the breadboard. These labels make it easy to follow directions when building a circuit. For example, all of these holes are in column C, and all of these holes are in row 12.
For the most part, you won't be concerned with these labels, the numbers and the letters at the top. That's to zero in on a particular location. But once you understand how the board works, you can put your components where you want, and that's what I would suggest you do. Once again, you understand how it works.
Hole C12 is where column C intersects row 12. There are also long strips on either side of your breadboard that are usually labeled with red and black or red and blue lines, and also a plus or minus sign. These are called either buses or rails and are used to deliver power to your entire circuit. Typically, the red one marked with a plus sign will connect to the positive battery terminal, and the black or blue one marked with a minus sign will connect to a negative battery terminal. Some breadboards, like this mini one, do not have power buses at all.
So, okay, yours doesn't, the little one doesn't have a power bus. The ones you will buy, the large that you will get, 2 on each side.
Some full-size breadboards have power buses that run the entire length of the breadboard, as indicated by the continuous unbroken red and black lines. Other ones have power buses that run half the length of the breadboard, as indicated by the breaking lines here.
And what I'm going to ask you to do, if you have this kind of board, and that's fine, is to put a little jumper wire from here to here, from here to here, from here to here, and from here to here, so that you have the entire length of the bus here, or the metal strips here. You'll see the metal strips run horizontally all the way across here. And I want you to make it go all the way across. We'll about that in a little bit.
This is a bit that needs to be powered by 2 different voltage levels. In order to use a breadboard, it really helps to understand how all the holes are connected. Let's take a look at hole A1 as an example. Remember that inside the breadboard are sets of 5 metal clips.
And it should be, maybe it goes without saying, but maybe not. Metal is a conductor of electricity. So if you put a component lead in here and you put another one here, they're connected together because the metal in the strip here connects them together.
This means that hole A1 is electrically connected to hole B1, hole C1, D1, and E1. If not connected, is that hole and they do not shape set of metal clips. It is also not connected to any of the holes on the other side of the gap in the middle of the breadboard. That's holes F1, G1, H1, I1, and J1.
He'll discuss this in a moment, but there's a gap or a channel running down the middle here, which is very important for when we put our integrated circuits in the project. But the bottom line is, as he's saying here, these 5 are fine, these 5 are, but there's nothing here that connects to these. And again, I'll show you that with your mini board in just a few
I'll
moments.
explain more about what this gap means in a little bit.
Okay.
This diagram shows all of the connections on the breadboard highlighted with yellow lines.
Notice again that these yellow lines are running all the way down here. There's no gap between here and here electrically. It's all the way through, and I think he'll open it up and show you in a moment.
Each set of 5 holes forming half a row, that's those on the left in columns A through E, and those on the right in columns F through J, is electrically connected. The power buses run vertically on the sides of the breadboard and are typically connected over more than 5 holes, although this can vary from breadboard to breadboard. The individual power buses are not connected to each other. Let's take a look at what...
And again, this is going to be your first project. It's going to consist of an LED, a resistor in series like this to light up the battery. You connect a little battery here and you're going to get that LED to light up.
All this means for a common demonstration circuit with a battery, a resistor, and an LED. When I turn the battery pack on, the LED lights up. Pretty simple. Now let's zoom in and see how I actually have everything connected on the breadboard. The battery pack's red lead is connected to the power bus on the right side of the breadboard. This is connected to a jumper wire that goes to row 5, which then goes to the LED, over to row 5 on the other side, to a resistor, to the ground bus, and then to the backplane lead. This diagram shows how electricity flows through the circuit using yellow arrows. This is
Now, I'm just going to say something briefly about this, and then we'll worry about it later, or if we worry about it at all. Current is the movement of free electrons in one direction. And there are two versions of current flow. One of them is called the electron flow version. The other is called the conventional current flow. You're going to see both from time to time, as you see right here. However, we will use the electron flow version almost exclusively. Once in a while, a conventional current flow will pop up. In the electron version, electron current flows negative to positive. In the conventional current flow, it flows from positive to negative. It doesn't matter, it's still electrons that are moving. But once in a while, it'll come up and you'll say, hey, wait a minute, this doesn't look quite right. You know, it's positive. So I just want you to be aware of it right now. We'll deal with it later.
a closed circuit or a complete path for electricity to flow. Remember that on each separate half of the breadboard, the holes in row 5 are electrically connected to each other. This means, for example, that I can take the leads of the LED and move them to different holes in row 5 and it will still light up. However, if I take the LED and move it to a different row entirely, like row 4 or row 6, it does not light up because there is no path for the electricity to flow. It has to be in row 5 to have that complete path. You can also reconfigure the entire circuit. For example, here I'm going to move the LED and the resistor over to the right side of the breadboard and then connect the battery pack's negative lead to the ground bus on this side. While this looks different, electrically it is the same circuit, so the LED is up. You can see that in this diagram by tracing the yellow arrows and noticing that there is still a closed path for the electricity to flow through the LED. Now let's take a look at some of the most common mistakes that students make when learning to use a breadboard. Here we have the demonstration circuit from the previous part of the video with a battery, a resistor, and an LED. At first glance, everything probably looks fine, but when I turn the battery pack on, the LED doesn't light up. You won't know why unless you look closely at the breadboard. When we zoom in, you can see that one of the LEDs actually in the lead the LED4. Rows 4 and 5 are connected. What are for electricity path to flow at LED 5? And then every time you always double check make sure your connections are in the right place. Another common mistake is not firmly pushing leads or wires into the breadboard all the way. Watch what happens if I pull this jumper wire out slightly so the connection is loose. The LED will still light up intermittently, but bumping the wire or shaking the breadboard can easily make the LED go out. To make sure the connection stays secure, you have to make sure the jumper wire is pushed firmly into the breadboard on both ends. The same goes for other components like the LED itself. You can see that if I pull the LED out slightly, it might look like it's actually pushed into the breadboard, but it's actually very loose and won't stay lit. This is because the leads aren't pushed in all the way, so to ensure it stays on, you have to make sure the LED is pushed firmly into the breadboard along with the rest of the components. The next common mistake will depend on the individual components in the project you're doing. Some components have polarity, meaning the direction they are facing matters. LEDs.
All right, basically the components that you will work with in electrons can be divided into two categories. Those that don't have polarity and those that do. Those that don't have the polarity, it doesn't matter what direction you put them in the circuit. And a resistor is a good example of a component that doesn't have any polarity. It has to go in the right spot, but it doesn't matter whether it's turned around or whatever. An LED is a good example of a component that does polarity. It must not only go in the right place, it must go in the right direction. In the case of an LED, if you put it in backwards, your project will explode. No, the good news is if you put it in backward, nothing will happen. It just doesn't work. So you just turn it around and put it back. And some of you might do that at first, and that's just fine. And that's the beauty of this solderless circuit board. They just pull it out and put it in.
A very common example. Notice how if I grab the LED and flip it around, it doesn't stay lit. If you look closely at an LED, you'll see that the two legs are actually slightly different lengths. The longer leg is the positive side and has to be connected to the battery pack's red lead.
We'll have a whole week on LEDs, so that's coming up quite soon, and we'll talk about that. But basically in electronics, if the leads of a component are of different lengths, the long lead is positive and the short lead is negative.
The shorter leg is the negative side and needs to be connected to the black lead. The resistor, on the other hand, does not have a polarity associated with it, so I can flip the resistor around and the circuit will still work just fine. When using a breadboard, you'll have to decide what type of jumper wires you want to use, and there are several different types available. First are these long flexible wires that come in many different colors and are usually sold in packs of at least 10. The wires themselves are very flexible, but they have metal pins attached to their ends that make them easy to press into the breadboard. While these wires can be very convenient for simple circuits, they can get very messy with complicated circuits, and as you add more and more to a breadboard, you'll eventually get a tangled nest of wires that can be very hard to keep track of.
I mean, they are nice to use. They are flexible and so on, but this is exactly what is wrong and what goes wrong. If the circuit gets to be of any complexity, you have this rat's nest of wires, and it just doesn't work.
Another option is to buy a jumper wire kit.
Now you have that. That was sent to you. You have different colored wires, and the wires the right size to go into the breadboard. It's 26 gauge, I think. It's the right size. It's pre-cut, pre-bent, and it's even color-coded. For example, with a short piece that's red. Red, what is red in electronics? What number is red? Anybody? Color code, think of it. What's the value? Red is 2. Red is 2. And the actual spacing on the board will be for 2 holes. The breadboard, in fact, it didn't mention this, interesting enough. The holes on the breadboard are 1/10 of an inch apart. They're all 1/10 of an inch apart. And so a red wire in here will be 2/10 inch apart. A blue one will be 6. But it's not, the color doesn't matter so much, as you'll see.
This is a small plastic container that comes with many different colors of wire that are pre-cut to certain lengths. The ends of these wires are bent down 90 degrees, which makes them easy to press into, which can make the circuit
No, that should be 6 pieces there.
Me llega uno, pero no se puede conectar.
If somebody would mute that,
No sé.
if you will mute.
Será por la.
Final option is to purchase special spools of wire called color wire, and use a tool called a wire stripper to cut them to length.
Pero agarra, no agarra nada. ¿Y por qué el de Carlos se agarra?
Le tengo que preguntar si tiene la contraseña al otro.
I'd like you to mute yourself there,
Just have to
please.
bend the ends of the wire down, and then you'll be left with a piece similar to what comes in the jumper wire kit that easily fits in. The advantage here is that you can buy several spools of wire of different colors and then cut them to any length you want, so you can color code your circuit. If you do decide to buy your own hookup wire, you need to make sure that you buy solid wire, stranded wire.
And he's going to point out that he was using stranded wire there. No. You want solid core. It's not as easy to bend, but that's the only way it'll go into the board.
Solid core wire has wire made of a single solid piece of metal that is very stiff and easy to push into a breadboard. Stranded wire is made up of multiple individual smaller strands, kind of like a rope. This makes
The advantage of stranded wire is it's easy to bend. But the disadvantage is when it comes to this board is,
the
as you'll
overall
see.
wire much more flexible, but the ends are also flexible and therefore much harder to push into a breadboard. If you were watching closely earlier,
Ahorita le voy a preguntar si tiene la contraseña al otro.
solid core wire. You can stranded wire and strands together. And that's what you need to do. It's still not the easiest way to go. Finally, all this time, you might have been wondering what this gap that goes down the middle of the breadboard is for.
Now, this is very important, this gap.
This gap is designed such that integrated circuits, sometimes just called chips, that come in a dual inline package, meaning they have 2 rows of pins, can fit nicely straddling the middle of the breadboard. When you have a new chip, you might need to bend the pins together slightly so they'll fit into the breadboard, but then you just have to line up all of the pins and press it in firmly, just like you would with any other component. This works great because now the pins on each side of the chip are each connected to their own row.
For example, the pin here, this pin 4 here, connect to pin 14, you have 4 holes remaining here, or 4 points that you can stick something in to connect to it.
What you don't want to do is put the entire chip just on one side of the breadboard.
Actually, what you don't want to do is pull it out like he's doing, because if you pull it out like that, it'll also stick around and stab you in the under your fingernail sometimes. So you might want to use a little screwdriver or something to pull it out. But what he's going to show you here is important.
So it's not straddling the gap. Remember that the pins in each row on either side of the breadboard are electrically connected to each other. So if you put a chip in like this, you're shorting out the 2 pins in each
Can
row.
you come downstairs
Yeah.
after you're done?
This one here is shorted out with this one. Just shorted out. It's connected words. You don't want to do that. It's got to straddle the channel. We're almost done here.
Integrated circuits come in many different sizes, and they all serve a special purpose. However, all of them will fit directly into a breadboard straddling the middle gap. You can find a written version of this tutorial along with other helpful electronics tutorials.
Okay.
Tutorials like how to use a multimeter and how to strip wire, all at our website, www.sciencebuddies.org. You can also go to our library, Science and Engineering Project.
Okay, that was the video. You, of course, can look at it anytime again, and you may want to do that. Are there any questions
Ahora sí.
at this point?
Anda la manga, le dije que se podía bajar.
¿El qué?
¿El Carlos?
No, sí. Pero ahorita aquí que
See, the basic board will be here.
No, la cosa de ayer es la parte no la estaba.
Okay, is somebody asking me a question, or are we?
Omar, mute your mic.
Yeah. There's a good bunch of you here. That's great. That's good. This is the bus strip that you'll be using when you build, when it goes all the way across. You just need to know that, and it'll work on both sides. These are the underneath. This is a board that's reasonably complex, put together. Again, this is what you're going to do. You're going to build the circuit. This is a schematic drawing, which shows you the symbols for a particular component represented by that symbol, which you'll come to know, and lines on the drawing which represent connections or wires or connections. Over here, we have a battery. This is a battery. This is a symbol for a battery. The long lead is the positive end. The short lead is the negative, as is true in electronics. This will be your 9-volt battery, and you'll be using your 9-volt battery clip. The black lead will go here. The red lead will go here. You'll stick your battery in the clip, and you'll be ready to go. This is a resistor, which I'll explain in just a moment the values here. This is a symbol for the resistor that you'll put in the circuit. Don't worry about this. This is a symbol for an LED, light emitting diode. The pointed end is the cathode, or the negative end, or the short lead. The other end is the anode, or the positive lead, and it's the long one. And again, if you get this wrong, you just turn it around. But the anode end is connected to the resistor. The cathode end goes to the negative end of the battery. The other end of the resistor goes to the positive end of the battery, and you're on your way. What I want you to do with this activity is to start out with a low value resistor around 150 ohms. You were given a packet of resistors, and I'm not sure whether you have 150 ohms in there, but you have something low like that. Doesn't matter. I want you to start out with that and note the brightness of the LED. And then you're going to replace that low value resistor with something that's a little higher. Resistors are there to limit the current flow in a circuit. Limit it. They're not eliminate it, but limit it. And the more resistance you have, the less current you have. And the less current you have, the dimmer the LED. So when you replace the 150 ohm with a 470 ohm, your LED should be a little dimmer because there's less current flow. They want you to move a 2.4K resistor, and then a 100K resistor. And then I don't think you have a 3.3 meg in there. It doesn't matter. The point here is I want you to go and keep increasing the value of the resistor and see what happens to the LED. If you have a 100,000 ohm resistor in your packet, it's going to be such a high resistance and so little current will flow that the LED won't even light. So this is a very important activity for you to do, very important, because number one, you learn to read a schematic drawing. This is about as simple as one as I could get to start out with, but you'll learn to read a schematic drawing. Number two, you'll learn how the solderless circuit board works. You'll see if you get it in, plugged in right and everything. And number three, you'll understand better the relationship between more resistance and less current indicated by the brightness of the LED. The LED is really just there to indicate that there's less and less current as the resistance goes up. So by all means, do this activity. And I'll show you something laid out in just a moment. Are there any questions about that? All right, let's go back here for a moment and look at, we're over here. We did this. This is the activity that you will be turning in. This is something I want you to look at. This is an information sheet. You'll notice it doesn't have a place for your name because it's nothing you turn into me, but it is something you look at. And I'm going to show you this in just a moment when I get out, stop sharing my screen and show it to you. But this is how your board works, your mini board. It's the same thing that we talked about here, but I'm just zeroing in on it. And you can see the back of it, how it's with all these little clips here. There's the channel. Here it is up front. I put an integrated circuit in the straddle of the channel, and I've got a few resistors here, and I've labeled them here. So this one is R1, this is R2, this is R3, this is R4, and I guess that's R5. And what I tell you is this. I say R1 and R2 are connected. So you should see how R1 and R2 are connected because they're in the same strip here, right here. I say R3 is not connected to R1 and R2 because the other side, so while it lines up here, it's not connected to these two because of the gap. R4 is not connected to any component. There's nothing else that's connected to it. R5 is connected to pin 2 on the IC integrated circuit. This is pin 1, 2, 3, 4, 5, 6, 7, 8. We'll talk about that later, how you identify the pin numbers on an IC or integrated circuit, but this is pin 2. And so R5 is connected to pin 2. Pin 2 takes one hole, takes up one hole, and then you've got this. And by the way, it wasn't said in the video, but it's very important. Understand that there's only one thing that goes in a hole. Don't try to jam more than one wire or lead into the same hole. You don't have to, and it won't work well. And don't try to do that. One per hole. Any questions? Well, if there are no questions, it means that one of two things is happening. Either this has been a brilliant explanation of what's going on, or you haven't the slightest idea what the hell I'm talking about. But I hope it's not. Let me get out of this view and let me stop sharing for a minute here. And you can see my.
This is Casey.
Oh,
I have
look
a
at all of
question.
Yeah, good.
Could you go over the polarity of LEDs again, please?
Sure. And again, we'll have a separate lesson on that coming up. But the LED has polarity, meaning it has to go in the right direction. It has an anode and a cathode. The cathode goes to negative, the anode goes to positive. On a basic LED, the way to tell which is anode and cathode is by the length of the lead. The longer one, it's not that much longer, but it is longer. The longer one will be positive and the shorter one will be negative. Most of the LEDs, well, the LEDs that you will get will either be 5 millimeter in diameter or 3 millimeter in diameter. The ones that are 5 millimeter in diameter will have a little flat spot which lines up with the negative lead or the short lead. The other end is positive. You'll see it on the lens when you hold it in your hand. The 3 millimeter lead, you can't really see that with the 3 millimeter ones that are smaller, but the length of the lead will be your indicator. And again, fortunately with an LED, if you get it in backwards and it doesn't work, you just turn it around.
Thanks.
Now, in order to see more of me, I think what you need to do, I go back to, I've been told if you want to see more of me, a bigger picture of me, which I want you to do in a second, I think you have to click it. You have to go up to speaker view and enter full screen. Well, I'm going to enter the full screen now, but because all I see is little me. I see a lot of you guys. That's great. This is the board that I showed you in the drawing there, in the sheet. This is exactly the board. In fact, I took a photograph of this and made it into that worksheet. With these boards, you can make these kinds of little projects. And you can see I've just taken a few of them and built little projects with them. You would have one board, so you'd build one project on it, and then if you wanted to go on to the second project, you'd have to take that one down and build another one. But I had a whole bunch of these little boards, and they were pretty cool. Now, there's one other thing I will be doing in a second, and that is opening up the sheet in front of me here, or the table in front of me. Let me show you something else. Now, this is a project built using the larger board. This particular project is a combination lock. And students have built this or a version of this in the class before, and you may build it near the end of the semester anyway. But you can see it's a little more complicated. In fact, this one's fairly complicated because the output is connected to a relay, which in turn is connected to a solenoid here, a door solenoid, which is a deadbolt Dulcin. And what I do is when I push the right code in here, that should activate. Let's see. You heard it snap and this pulled in, the door opened up and you walked inside and any other button will disengage it. Probably can't. I'm going to lay it out on the table in a minute, but you get the idea. You have to press the code, the right code in the right sequence for that to happen. Let me do it again. 8, 4, 3, 9. Wham. This whole thing's a power supply to run the solenoid, which is this door jam here. So this can get to be reasonably complex like that, which is okay. All right, let's see. Move this over here. Okay. Now, I want to, hang on just a second. Let me see. Okay, let me see where we are. Hang on just a second. Oh, good. It's exactly 9 o'clock. Okay. One thing I wanted to mention about resistors that I didn't when we were talking about the color code and so on is that resistors come in different sizes. And the size, the physical size, has nothing to do with the value in ohms. It has to do with the wattage or the ability to dissipate heat. And the larger it is, the more heat it will dissipate. The resistors you received are 1/4 watt. Maybe you got a 1/2 watt in there or something, but you basically have a 1/4 watt. And these are what they look like. And it's basically the larger it is, the more surface it has to the air and it can cool down and so forth. They can get pretty small. They can get to 1/8, 1/10. But for the most part, you'll be working with 1/4 watt resistors. And again, the 1/4 watt resistor has nothing to do with the value in ohms. An entirely separate issue. A couple of you have asked me about a book. And I understand that, believe me, I understand you wanting a textbook. There's no required text, but if you're going to use a text, if you want to get one, I wrote this in the note that I sent you. This is a book on electricity. It's a pretty good one. It's under $50. It'll give you pretty much what you need here. And again, I've already written, I've given you the information on this, the ISBN number and so on. Again, it's not required. It's not required. But some of you may want it anyway. Are there any questions at this point? Okay, so basically what we've done today so far is to talk about solderless circuit board. And I would like you to go ahead and do that activity as soon as possible and send me the sheet as you've done, as you've been doing, and build it. And let's see how well you can get that working. I don't need to see it working. If you want to send me a picture of it working, fine. But I don't need to. I need you to answer the questions and so forth. And again, there are 2 activities this week, like there were last week. There will be times when there'll be 3 or 4 things for you to do. And so don't wait until Sunday evening to do them. And you did fine. You did fine. I got a couple in late Sunday, but that's okay. It's still perfectly legitimate. You're doing fine, but don't wait till the end to do it. I would imagine you'd want to get onto it anyway. So that's what we've done. So let's spend the next few minutes, next 10 minutes or so, talking about the solder kit that you're going to do. And with that, I believe I had let's see. We go back to here. Solder prac kit. Let me see if I had a video here. I'm not sure if I did. This is the worksheet that you're going to turn in. It just asks you a bunch of questions here that that you'll pick up from reading the material in the manual. Okay, so that's all that is. This is what you will do. So there are 2 sheets that you will turn in this week. One was the previous one I showed you on the side of the circuit board. Then there'll be this one too. I'm a little bit surprised that I didn't have a video I didn't have a video on soldering. I know I have plenty of them, but all right, anyway. All right, so let's take a look at in your kit you have solder. Actually, you have two types of solder that you've been given. Excuse me. So in the kit itself, you have this tube of solder. And the solder comes out here. You can see what it's not a big deal to do. And you just pull it out, put it in your hand, and you get your soldering iron in there. I showed you this last week, and you solder. This is lead-free solder. It's the new kind of solder. It doesn't have any lead, so that's good from a health standpoint. But it's harder to work with. It is harder to work with. You need more heat, but you can do it. That's why it's there. However, I did give you in your packet, in this packet here, I gave you a couple of wines of solder here. And I'll almost certainly be sending you more of this. This is not lead-free, but it won't kill you. And you might want to start out with this solder. You could cheat. This is all experimenting on your part. You're learning, you're practicing. But you might want to start out with this solder. It's a little easier to work with. I'll say from a safety standpoint, I'll make this general statement: when you're done soldering, wash your hands. Okay. If you don't, and you pick up a donut and you start eating it, you probably die from the donut. No, don't worry about that. And I said, show you guys, I tell you, look what, my wife said to me the other day, when I married you, you had hair all over your head. It's thick, hunky hair. So when I married you, you weighed? No. She still weighs pretty close to what she was when I married. But if you solder every day like this, you'll get to be my age, you'll probably lose your hair. Correlative, but not causative. But it's a good idea. Don't chew on this stuff. Okay. I can't emphasize enough that with this kit, you're practicing. And so when you start to make solder connections, I wish I was with you. Just to see, when in class, I could walk around and I could see, and I could take my magnifying glass and I could look at your solder connections and see that they're nice and shiny. And if they're not, reheat them or do, but I'm not with you. So kind of on your own on that. Read the manual, look at the manual's instructions on how to solder. And then I told you there are 4 steps, and I put that in the summary for last week. You take the soldering iron, you heat the joint, you come from the other side with the solder, you watch it melt, you remove the solder, wait 1 long second and remove the heat. And your solder connection should be nice and shiny rather than dull gray. If it's dull gray, you repeat it, you just redo it. Do as much as you want and can and care to in this solder activity kit so that you feel comfortable about soldering. As I mentioned twice now, when we were in person, we didn't do anything nearly this extensive. It was 1 day practice solder. And I told the students, look, if you want to practice at home, take the iron home, take some more solder. And so you're being asked to do a lot more with this solder kit than we did in the past. And all I'm asking you to do is to get comfortable with it. If you feel that you've done enough, put it aside. it's true that there are two parts. Again, the practice stuff, cutting the wire and all that. And then there's the actual project with the two LEDs flashing. And you probably want to get there at some point. You want to show your kids or show your little brothers and sisters. Are there any questions about what I expect from that?
No.
Just practice, enjoy it, you know. Most people like to solder as long as they don't have to do it 8 hours a day. It does take some practice. Be sure to put your components in the board in the right direction. There's the component side, which is blue, and the leads come out on the other side. I'll be honest with you. When I did my first project like this, I got it backwards. It's 50 years ago, but I got it backwards.
Did they have LEDs back then too?
Yes, they did. They did, and they were very expensive. But they did have LEDs. But I soldered on the wrong side. Look, I want to tell you something. When I was in high school at Van Nuys High School, anybody here go to Van Nuys High School? That's too bad, because that's an automatic A. It's an automatic A. Did anybody here go to Burbank High School? You did. I taught at Burbank High School for 13 years. Automatic A, Alex. You can go home.
Yeah.
You can just automatic A, as long as you do A work.
Okay.
Anybody go to Burroughs? I did my student teaching at Burroughs. Anybody go to Grant High School? Nobody here at Grant? That's good, because you might as well drop the class. What happened? When I was at Van Nuys High School, I had a girlfriend. Her name was Tina Strozer. Cutest little thing. The only trouble is, well, I thought of her as my girlfriend. She didn't think of me as her boyfriend. And then Grant High School opened up and she transferred to Grant High School. And I've been mad at Grant High School ever since. Now, my students usually say, it's time to get over this, Mr. Reed. It's been over 50 years. And I've been married for 54 years. Still have my cute little girl. I don't tell her the story, though. Anyway, why did we get off on that? What was I trying to, what point was I trying to make? I don't know. But anyway, okay, here's the point I was making. When I was at Van Nuys High School, I wanted to be an architect. I took lots of drafting courses, and I wanted to be an architect and go to USC. But at USC, it cost $35 a unit. Do you know what it costs today? Almost $2,000 a unit. This course would cost you almost $6,000 at USC. Back then, it was $35 a unit. It was too much. That wasn't the only reason. When I was a senior, I'd taken all the courses I needed to get into college, and the counselor, who was half-time counselor and half-time electronics teacher, put me in his electronics class. And I got a C in the class and was glad to get it. I didn't know what the hell I was doing. My point is, I wasn't born with a capacitor in my hand or any of this knowledge. I had to learn this. Later on, I got really interested in electronics. It did. But not at the beginning. I got a C in the class. So, you know, you learn. You learn. And that's what you're going to do. You learn. As I was saying to a couple of you before the class started, you know, the beauty in electronics is that you can get more for less now. Every year you get more for less. You can buy a multimeter today for $10, $12, $15 that would cost you $200 10 years ago. LEDs a penny a piece. Okay, are there any questions before we sign out?
Yep.
You ready to build that little solderless circuit? Go ahead and do that. And then practice your soldering, and I'll see you on Thursday. And we have more to talk about and more to do. I've got another class now.
I have a question.
Yes, who? Yes.
Yeah, I I did my solderless assignment, and then after these assignments, my the what do you call it? The resistor code I had, you gave me 22 ohms instead of 150.
Yeah.
I couldn't find 150 resistor
Okay,
code.
are you referring to the one we just talked about, the solderless circuit board one?
Yes.
Yeah, as I say, you probably didn't. Just go from smaller to larger, or the lower value to larger, and see what happens.
No, I just reviewed all the colors and just wrote them down on the color.
Well, you have a
code.
bunch of resistors that I sent you, and you also have this packet of resistors for your solder kit. You can use some of those. In the solderless circuit activity, just take it from the lower values to the higher values. Okay?
Okay. And then the bad thing, I blew out a LED light. This one.
How'd you do that?
I don't know. I forgot. I just put it in too soon, and then I heard like a spark, and I'm like, remove it, and I burnt my
Okay.
hand.
Well,
And-
what you did undoubtedly is this. Look, LEDs require around 2 volts, 2.2 volts. If you put any more voltage across them, you're going to blow them out. And you probably did that. That's why we use a current limiting resistor. And in this project that you built, I mean, in this solderless circuit board activity that you put together, you have a resistor in there. And you have a resistor for a reason. And I think it starts out, as I said, with 150 ohms. If you go down to nothing, if you don't put it in there, you will burn it out. Shame on you. But you have a bunch of other LEDs, don't you?
Yes.
And again, I didn't say you use whatever LED you want there, whatever color you want. Start with red usually. And so once you build that and it's working, I mean, it's just lit up, that pull the LED out and put a yellow one in, or put a blue one or blue one. That's the idea behind this solderless circuit board. You can just change your color, change the LED.
Okay.
color. Okay.
I learned my lesson.
Yes, and that's
Bad way.
yeah. Well, no, but you know, yeah. In this case, it's no big deal. They're a penny a piece, as I say, as long as you didn't hurt yourself. But yeah, that's kind of how you learn.
No, I just forgot to just take it out earlier without it.
Okay.
I forgot to put in the resistor for it at the same time.
Well, as you say, you learn. Okay. Are we? Any other questions?
Yeah, there's one in the chat. They wanted to go over the breadboard diagram.
Well, okay. The diagram. What do we want to do with that again? As I say, I would suggest again you look at that video. I think that's a pretty good video. Some of these videos are better than others, but I think I chose a pretty good one there that explains how that works. And you're going to learn too here. You try to build that circuit, and if it doesn't light up, you ask yourself, what's wrong? Do I have a good 9-volt battery? Have I connected it correctly? Is my LED in backwards? And most important of all, do your pins line up? And I would suggest, anybody who's chatting me on that, I would suggest that you look at the video again. Just go ahead and work through that video. And if you still have any questions after that, just email me or call me. Let me know.